Volumetric efficiency compares the volume of air entering a cylinder during intake to the internal volume of the cylinder when the piston is at bottom dead center. It is usually expressed as a percentage. In a naturally aspirated engine, one without forced induction, volumetric efficiency can never be 100%. This is because of the resistance to the airflow that occurs at the carburetor, manifold, and the intake valve. With forced induction, the incoming air is compressed so that a greater volume and mass of air is forced into the cylinder during the intake stroke. That takes the volumetric efficiency to above 100%. Sound travels through the air by producing pressure waves, areas of high pressure and areas of low pressure. The rate at which these waves reach our ears is called frequency. It is measured in cycles per second, where a cycle is the distance between waves or wavelengths. The higher the frequency, the higher the pitch of the sound. The range of human hearing is approximately from 20 cycles per second to 20,000 cycles per second. An engine produces sounds across a wide range of frequencies. The mufflers and resonators in the engine exhaust system reduce these sounds to an acceptable level. Thermal expansion refers to the way some materials expand when they are heated. The same amount of heating can produce different amounts of expansion in different substances. Components that are subject to heating have to allow for this expansion in their design. An engine exhaust system is subjected to very hot exhaust gases, so its components expand and contract as they heat and cool. Mountings in the system are designed to allow this to happen. A resonance is a form of echo. Sound waves or vibrations in one object causes sound waves or vibrations to occur in another. The induced vibration is sometimes called a sympathetic vibration, and the second object is said to resonate. A sympathetic vibration is called a natural vibration of an object. That means it's more likely to vibrate at that frequency than another. With this glass, just the right note sung at the right frequency started it vibrating with disastrous consequences. It can become a problem if the sympathetic vibration adds to the original vibration. In an exhaust system, that means more sound waves, which means more noise. To reduce this, a resonator is fitted in the exhaust to act as a sound dampener and reduce the effects of the resonating sound waves. Back pressure in an exhaust system refers to a buildup of pressure in the system that interferes with the outward flow of exhaust gases. This area of high pressure acts as a kind of wall to stop gas flow. It can be caused by a blockage in a muffler or a similar restriction.
This section examines the diesel induction system, beginning with the four-stroke engine. The two main components of the intake system are the air cleaner and the intake manifold. But in a diesel engine, since fuel is delivered separately and the intake system carries air only, there is less restriction in the intake of the air than in a carbureted system. Also, since the diesel engine doesn't have a carburetor, it has no throttle plate. Some diesels use a pneumatic governor with a butterfly valve at the entrance to the inlet manifold. Diesel engines often have more than one air cleaner. The intake system of the diesel engine can be used to increase engine output. This can be done by increasing volumetric efficiency, that is, by increasing the amount of air that enters the cylinders. Output can also be improved by using large, free-flowing intake manifolds, and by increasing the number or the size of inlet valves per cylinder to admit more charge into the combustion chamber. Another method is to use forced induction or supercharging to pressurize the intake of the air and force more air into the cylinders. Let's look at the intake system for a two-stroke diesel engine. There is only a very short time at the end of its power stroke to scavenge the exhaust gases and refill the cylinder with air. To achieve this in the time available, two-stroke diesels use an engine-driven air pump, usually called a blower. It pressurizes the air so that when the inlet ports open, air from the blower enters the cylinder and helps scavenge the exhaust gases. Some two-stroke diesel engines use a turbocharger, which feeds air under pressure to the blower. This section examines carbureted intake systems. On a carbureted engine, the intake system is part of the fuel system. The main function of the intake system on a petrol engine is the delivery of the required amount of the mixture of air and fuel. In a basic system, air enters the air cleaner for filtering, then passes into the carburetor, where it mixes with the required amount of fuel. This air-fuel mixture then enters the intake manifold and finally the cylinder. The same basic principle applies on the rotary engine. On all carbureted systems, the intake system can be crucial in increasing engine output. This can be done by increasing volumetric efficiency, that is, by increasing the amount of air that enters the cylinders. This can be achieved by using a large inlet valve or multiple valves to admit more charge into the combustion chamber. By using large free-flowing intake manifolds. By using extra carburetors. This section examines the electronic fuel injection intake systems for petrol engines. The intake system is part of the fuel system. Its main function on a petrol engine is to deliver the required amount of air-fuel mixture. Air is filtered by passing through an air cleaner. Information from many parts of the engine is fed into an electronic control unit, which then determines how much fuel should be injected for those exact conditions. Fuel is supplied under pressure from an electric pump to electronically controlled injectors. There are two basic electronic fuel injection systems, single point and multi-point. In the single-point system, the intake manifold carries an air-fuel mixture. Fuel is sprayed into the top center of the intake manifold. This manifold is similar to that on a carbureted system. In a multi-point system, the intake manifold carries air only. Multi-point injection has a fuel injector in each inlet port going to each cylinder. Petrol is sprayed into each port in front of the intake valve. The intake system can be crucial in increasing engine output. This can be done by increasing volumetric efficiency, that is, by increasing the amount of air that enters the cylinders. In fuel injection systems, this partly occurs automatically because of the increased efficiency of fuel injection compared to carbureted systems. Output can also be improved by using large, free-flowing intake manifolds, and by using larger valves to admit more charge into the combustion chamber. Another method uses forced induction or supercharging to pressurize the intake system and force more air into the cylinders. This section examines the diesel induction system, beginning with the four-stroke engine. The two main components of the intake system are the air cleaner and the intake manifold. But in a diesel engine, since fuel is delivered separately and the intake system carries air only, there is less restriction in the intake of the air than in a carbureted system. Also, since the diesel engine doesn't have a carburetor, it has no throttle plate. Some diesels use a pneumatic governor with a butterfly valve at the entrance to the inlet manifold. Diesel engines often have more than one air cleaner. The intake system of the diesel engine can be used to increase engine output. This can be done by increasing volumetric efficiency, that is, by increasing the amount of air that enters the cylinders. Output can also be improved by using large, free-flowing intake manifolds, and by increasing the number or the size of inlet valves per cylinder to admit more charge into the combustion chamber. Another method is to use forced induction or supercharging to pressurize the intake of the air and force more air into the cylinders. Let's look at the intake system for a two-stroke diesel engine. There is only a very short time at the end of its power stroke to scavenge the exhaust gases and refill the cylinder with air. To achieve this in the time available, two-stroke diesels use an engine-driven air pump, usually called a blower. It pressurizes the air so that when the inlet ports open, air from the blower enters the cylinder and helps scavenge the exhaust gases. Some two-stroke diesel engines use a turbocharger, which feeds air under pressure to the blower. This section examines air cleaners. An air cleaner filters air that passes through it to stop harmful particles reaching the engine. The air cleaner on a carbureted engine can be on top of the carburetor, or beside the engine, connected to the carburetor by a hose or duct. Position is usually decided by how much space there is, or bonnet profile. On some electronically fuel-injected engines, the air cleaner is on top of the throttle body, similar to a carburetor. Other air cleaners are connected by ducts. Diesel engines often have more than one air cleaner. This may be due to their severe working conditions. They're usually mounted away from the engine to obtain cleaner, cooler air. A lot of air passes through the intake system into the engine. In a petrol engine, it's about 15 times the amount of fuel by weight. By volume, that's about 11,000 times more air than fuel. The air-fuel mixture enters the engine, so the air needs to be clean. Any abrasives that enter the engine can cause wear and damage. It also has a silencing effect, muffling noise produced by the air entering the engine. It can act as a flame trap, so if a petrol engine backfires, the air cleaner can contain the flame within the intake manifold or the carburetor. The most common air cleaner is called a dry element type. It has a replaceable dry element of pleated paper or cellulose fibre that doesn't need to be wet or use oil to act as a filter. The paper is pleated because that gives a much larger surface area in the space. The element is designed to be fine enough to trap impurities, but porous enough to let air through easily. Most heavy-duty air cleaners incorporate a cyclone-type pre-cleaner. It collects larger particles from the air before it enters a dry element cleaner. It can be mounted directly onto the air cleaner unit, or the cyclone principle can be incorporated into the main air cleaner element. This dry element cleaner is fitted close to the engine and is linked to the cyclone system by a duct. The name cyclone comes from angled vanes that give the incoming air a swirling motion. Centrifugal force throws the heavier dirt particles outwards. They can collect in a separate bowl at the bottom of the cleaner. In the single unit cyclone element, it collects at the end of the air cleaner case, where it can be emptied out manually or automatically. The air then continues into the dry element air cleaner. An efficient cyclone pre-cleaner can remove up to 90% of particles before they reach the main element. An air cleaner on a multi-point electronic fuel-injected engine usually has a different shape from that on a carbureted engine, but it serves the same purpose. In many vehicles, the air cleaner is mounted where it can get cool, clean air. This air is then carried to the throttle body by a long, flexible duct. Inside the air cleaner, a filter element of pleated paper filters the air and reduces noise. Some electronically fuel-injected systems have an airflow sensor after the air cleaner element. It accurately measures all air entering the engine and adjusts the air-fuel mixture accordingly. So it's essential there are no air leaks, or it will upset this mixture. This section examines intake manifolds. The intake manifold is usually a metal casting with several tubular branches, though it can also be made of a special plastic. In carbureted engines, the intake manifold carries the air-fuel mixture into the engine. The cross-sectional area of each tube needs to be kept small to maintain the high air speeds that improve vaporization. At the same time, it cannot be too small, since that restricts the airflow to the engine at higher speeds. Electronic fuel-injected engines with throttle body injection also have intake manifolds that carry air-fuel mixture. With multi-point injection, the intake manifolds carry air only, and the cross-sectional area of the tubes can be larger. More air can flow and the engine can produce more power. Fuel is injected into the intake ports of the cylinder head. This cylinder head has intake and exhaust manifolds for a 4-cylinder carbureted engine. It is a cross-flow head. That means the intake manifold is on one side and the exhaust manifold is on the other. On many cars, the intake manifold has a mounting for the carburetor and a flange that bolts onto the cylinder head. It has a branch for each cylinder to carry air-fuel mixture into the combustion chamber. This intake manifold has a water jacket under the carburetor mounting. Hot coolant from the cooling system flows through the water jacket and heats the manifold. Heating is required in a carbureted engine to provide better vaporization of the air-fuel mixture. This fuel-injected engine manifold has a plenum chamber that provides a reservoir of air and helps prevent interference with the flow of air between individual branches. It also acts as a silencer. On this primary manifold, the intake pipes are fixed in length. Other kinds of manifolds have extra valves to change the effective pipe length. They may be computer controlled by the engine management system to open at a specified engine speed and extend the torque output. A diesel engine intake manifold carries air only, not fuel, and since no fuel is vaporized in the manifold, it isn't heated. Some diesels use a pneumatic or air-operated governor with a butterfly valve at the entrance to the inlet manifold. This butterfly valve is only used to operate the governor. It is not a throttle butterfly valve as seen on petrol engines. This section examines intake air heating. Normally, the air entering the air cleaner is cold. Cooler air is more dense, that is, it contains more oxygen, and that should help the fuel burn more efficiently. But fuel doesn't vaporize very well in cold air. Since an enormous amount of heat passes through the exhaust manifold, many carbureted engines capture some of it with a shroud around the exhaust manifold. This heats the incoming air to improve fuel vaporization. This heated air then enters the air cleaner. Once an engine is hot, it may no longer need the incoming air to be hot, so the amount of hot air entering the engine needs to be controlled. On vehicles with emission controls, air cleaners use a valve to control how much hot air enters the air cleaner. This valve can be a simple thermostatic type. When the engine is started, only heated air is used. As engine temperature rises, the valve opens and provides more and more air at normal temperature. This ensures that the temperature of the air supplied to the engine stays fairly constant. Another way to control the amount of hot air is to use a vacuum motor and a temperature-sensitive valve that is mounted inside the air cleaner unit. When a cold engine is started, this valve allows vacuum from the intake manifold to reach the vacuum motor. This unrestricted vacuum acts on a spring-loaded diaphragm attached to the control valve. The valve opens fully and admits hot air to the air cleaner. As the temperature rises, the temperature-sensitive valve reduces the vacuum to the diaphragm. This in turn reduces the opening of the control valve and allows cooler air to blend in with hot air from the shroud. This section examines forced induction. One way to improve engine output is to increase the amount of air-fuel mixture that is burned in the cylinder. That means increasing volumetric efficiency, or how much air is delivered to the engine. This is done by what is called forced induction. Forced induction increases air pressure in the intake manifold above atmospheric pressure. An engine using forced induction can have a volumetric efficiency above 100%. A turbocharger uses energy that's normally wasted through the exhaust. Exhaust gases enter a turbine and make it spin. The more gases, the faster it spins. A shaft connects the turbine to an intake compressor. It compresses the air and forces it under pressure into the intake manifold. The turbine operates at very high temperatures and with the compressor can rotate at well over 100,000 revolutions per minute. So they both need a good supply of clean oil to lubricate their bearings and carry heat away. Some engines also supply coolant to the turbocharger body to improve cooling. On petrol engines, higher and higher engine speeds mean more and more exhaust gases, and that makes the turbocharger force more and more air into the cylinders. This can damage the engine. To control this, a device called a wastegate is fitted to the exhaust inlet of the turbocharger. When air pressure in the intake manifold reaches a preset level, it automatically directs exhaust gases away from the turbocharger. The wastegate can also be computer controlled to reduce intake air pressure in the event of detonation or knocking. An emergency relief valve may also be fitted so that if the wastegate should fail, it can prevent an abnormal rise in manifold pressure. Since the turbocharger uses the energy of the exhaust gases, there is a short delay between when the driver opens the throttle and when maximum power is available. This is turbo lag, and on larger engines it's quite noticeable. Because a turbocharger recycles heat energy that would otherwise be lost to the engine, it can seem to be offering additional energy for nothing. But a turbocharger can introduce problems of its own. The extra heat and power it generates can put an extra load on the engine's cooling and lubrication systems. This is provided for by the manufacturer. As the air passes through the turbocharger, it heats up. But hot air is less dense than cool air, so it tries to expand again, and some of the benefits of compressing it are lost. To stop this and improve efficiency, some engines use an intercooler to cool the compressed air. It fits between the turbocharger and the engine. It's usually air-cooled. This section examines automotive exhaust systems. During engine operation, each time the exhaust valve opens, pulses of hot exhaust gases are forced into the exhaust manifold. These hot, rapidly expanding gases produce a lot of noise, some of it at very high frequency. The exhaust system does several jobs. It has to reduce the noise of the exhausting gases to acceptable levels. It has to discharge the gases safely, far enough away to prevent them re-entering the vehicle. Some of these gases are highly poisonous. In an enclosed space, carbon monoxide can cause death in minutes. It is odorless and colourless, which makes it difficult to detect, and removing it is especially important. In modern vehicles, the exhaust system also assists in keeping harmful emissions to a minimum. The exhaust system is designed to enhance engine operation. A well-designed system can improve drivability and performance. In this simplified model, burned gases exit the engine through the exhaust port and pass into the exhaust manifold. The first pipe is usually called the engine pipe. It is connected to the outlet of the manifold, which carries the exhaust gases to the muffler, which reduces exhaust noise. Exhaust gases are then discharged through a tailpipe, usually at the rear or sometimes above the vehicle. This section examines the exhaust manifold. The exhaust manifold is bolted to the cylinder head at the outlet of the exhaust ports. On passenger vehicles, the exhaust manifold is usually made of cast iron. Sometimes there is a separate passage for each exhaust port. The length of the passages in the exhaust manifold should be designed so that pulses of exhaust gases from one cylinder assist the flow of gases from another. It has large tubular sections to improve gas flow, and no sharp bends to slow the gases down. As well, the exhaust manifold must be shaped to allow for the location of the engine and the bodywork of the vehicle. Some vehicles use heat shields to protect nearby components and the passenger compartment from the heat radiated from the exhaust components. This section examines exhaust pipes. The engine pipe is attached to the outlet of the exhaust manifold. It can be designed to branch in various ways. On this engine, the exhaust gas from 3 cylinders is fed into each engine pipe. The system needs flexible mountings and sometimes flexible joints to allow for engine movement and prevent noise and vibration being transmitted into the vehicle body. On some front-wheel drive systems, the exhaust system is designed to be strong enough to form part of the engine mounting system. Rubber mountings are popular because of rubber's natural dampening effect. They also allow for thermal expansion during use. This section examines extractors. Some exhaust systems have extractor pipes, sometimes called headers, one pipe for each exhaust port. They are designed with sweeps that stop restriction. The extractor pipes also provide a scavenging effect, helping remove exhaust gases from the cylinders. The outgoing pulse from one cylinder is timed to arrive at the junction at exactly the right time to help draw out the pulse from another cylinder. They are widely used on high-performance vehicles. This section examines mufflers. The muffler is located in the exhaust system between the exhaust manifold and the exhaust outlet. It is usually made of sheet steel coated with aluminium to reduce corrosion. Some are made of stainless steel. A muffler contains perforated pipes, baffles and resonance chambers. Many also contain sound-absorbing materials such as fiberglass or wire wool. The muffler slows down the gases and breaks up the pulsating sound waves and so reduces the noise. It must cause as little restriction as possible. Poor design can cause excessive back pressure that will slow down the escape of the exhaust gases and reduce engine performance. Some mufflers combine baffles and pipes to change the flow of gases without restricting them. Gases enter through the inlet and must reverse their direction of flow before they exit through the outlet. This is called a reverse flow muffler. Some mufflers use double outer skins to minimize heat and noise transmission. Some exhaust systems use a resonator as well as a muffler. It looks like a muffler, but it usually has a straight-through design and it contains sound-absorbing material. It's designed to remove resonance levels that mufflers can't remove. This section examines catalytic converters. A catalytic converter is used to convert unacceptable exhaust pollutants such as carbon monoxide, certain hydrocarbons and oxides of nitrogen into less dangerous substances. Three-way converters convert hydrocarbons and carbon monoxide to water and carbon dioxide. They convert the oxides of nitrogen back into nitrogen and oxygen. Older catalytic converters converted hydrocarbons and carbon monoxide to water and carbon dioxide, but were not able to convert the oxides of nitrogen. A catalytic converter fits into an exhaust system like a muffler. It is located close to the exhaust manifold so that it can reach its operating temperature as soon as possible. Leaded fuel must not be used in an engine with a catalytic converter because lead will contaminate the catalyst and prevent it doing its job. It operates by starting and then maintaining a chemical reaction in the exhaust gases. It usually operates at higher temperatures than a muffler. It has a heat shield to prevent heat radiating to bodywork and other parts. This section examines flexible connections. This is a flexible connection between an engine pipe and an intermediate pipe. It is used close to the engine. Its main functions are to allow engine movement and reduce vibration without passing it along the exhaust, especially in front-wheel drive vehicles. It also helps with the alignment of the pipes.